40 light-years from here, there is a world where the ground is molten rock, the sky may be raining glass, and a single year lasts 17 hours and 41 minutes. Not 17 days, not 17 months, 17 hours. If you moved there this morning, you would have already lived through a full calendar year by the time you went to bed tonight. And nobody expected a planet like this to be doing anything like this, because for over a decade, this world carried a nickname that spread further than almost any other object in modern astronomy: the Diamond Planet. A super-Earth supposedly built out of carbon, crushed into a jewel the size of a world. That story was published in a real scientific journal, by real scientists. And then something happened that almost nobody outside the field ever heard about. Stick around, because I'm about to walk you through what scientists actually just confirmed about 55 Cancri E. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration. Let's go back to where this story actually begins. In August 2004, a team led by astronomer Barbara MacArthur at the University of Texas at Austin announced a new planet. It was not a glamorous discovery. It came out of radial velocity data. That means years of watching a single star wobble, measuring the tiny shift in its light as an unseen object tugged it back and forth. The work is slow. It is mostly spreadsheets. You do not see a planet. You see a number that will not sit still. The star was 55 Cancri. It sits in the constellation Cancer, about 40 light-years away. And here is the part people usually skip. You can almost see it yourself. Under a genuinely dark sky, with no moon and no city glow, 55 Cancri sits right at the edge of naked-eye visibility. It is not a distant abstraction. It is a faint point of light that human beings have been looking past for as long as there have been human beings. The team found a planet orbiting it that was small, dense, and absurdly close in. They measured its year at roughly 2.8 days. That number was wrong. 6 years later, in 2010, a graduate student at Harvard named Rebecca Dawson, working with Daniel Fabricki, did something unglamorous. They went back through the existing data. No new telescope, no new mission, just a careful reanalysis of numbers other people had already collected. They found an aliasing error, a rhythm in the observations that had disguised the planet's true beat. The real orbital period was not 2.8 days. It was 17 hours and 41 minutes. That correction changed everything. Because a planet that close to its star has a very specific property. It passes directly in front of the star, from our line of sight, roughly every 17 hours. Which meant it could be caught in transit. Which meant it could be measured. In 2011, 2 separate instruments caught it. The Canadian MOSE satellite, a space telescope roughly the size of a suitcase, and NASA's Spitzer Space Telescope. They watched the star dim by a fraction of a percent, on schedule, over and over. For the first time, we had a real size for the planet, and combined with the mass from the wobble data, that gave us the one thing astronomers actually want: density. Here is the step-by-step chain that turned a dot of light into a diamond. You measure how much the star dims. That tells you the planet's width. 55 Cancri E came out at roughly twice the radius of Earth. You measure how much the star wobbles. That tells you the planet's mass. It came out at roughly 8 times the mass of Earth. Now you divide. Mass over volume gives you density. And density is a fingerprint, because different materials pack differently. Iron is heavy, rock is lighter, water ice is lighter still. 55 Cancri came out dense enough to be rocky, but not dense enough to be a scaled-up Earth. There was room in the numbers for something else in the interior, something lighter than iron but heavier than water. In October 2012, a team led by Niku Madhusudan, then at Yale, published a paper in the astrophysical journal Letters, proposing an answer. What if the planet formed out of material that was unusually rich in carbon? The reasoning was straightforward. Planets are built from the leftovers of the star that made them. If the star's chemistry is carbon-heavy, specifically, if it has more carbon atoms than oxygen atoms, then the disk of debris around it will be carbon-heavy too. And a rocky planet assembled from carbon-heavy debris does not end up made of silicate rock like Earth. It ends up made of carbon compounds, graphite in the outer layers. And below that, under enough pressure, carbon does what carbon does. It becomes diamond. The models suggested that up to a third of the planet's mass could be diamond, a third of 8 Earth masses. That is the headline. That is the number that went around the world. And to be clear about what happened next, the paper was legitimate. The reasoning was sound. The scientists did the work honestly. The problem was not the model. The problem was one input number. Understand what we are actually working with here. 40 light-years. That number sounds small next to the rest of the galaxy. And it is. In our neighborhood, 40 light-years makes 55 Cancri, practically a neighbor. But light from that star left in the mid-1980s, and no spacecraft humanity has ever built could cross that gap in less than several 100,000 years. We are never going there. Not with any technology that currently exists on paper. Everything we know about this world, we know from light. And not much light. The planet does not glow on its own, in visible wavelengths that we can separate out. It is drowned in the glare of a star, tens of thousands of times brighter. Trying to see it directly is like standing in Los Angeles and trying to spot a candle sitting next to a lighthouse in San Francisco. So astronomers do not look at the planet, they look at the star, and they subtract. They watch the star's brightness with extreme precision. When the planet passes in front, the star dims by about 0.04%. That is the entire signal, 4/10,000ths of the light. Then they wait for the planet to pass behind the star, a secondary eclipse, and they measure the tiny drop again. That drop is the planet's own heat being removed from the total. Subtract one from the other, and you get the temperature of the planet's dayside. Every claim in this story rests on differences that small, which is exactly why one number in the chain being slightly off can change what an entire planet is made of. And in 2013, that is precisely what happened. The diamond model depended on the carbon-to-oxygen ratio of the star. If that ratio was above 1, more carbon than oxygen, carbon planets become plausible. Below 1, and you are back to ordinary rock. The 2012 model used a stellar carbon-to-oxygen ratio slightly above 1, based on the measurements available at the time. In 2013, Johanna Teskey and colleagues remeasured it. Stellar abundances are notoriously difficult. You are reading the chemistry of a star from absorption lines in its spectrum, and the answer depends on your model of the star's atmosphere, your line list, your assumptions about temperature. Their revised value came out around 0.78, comfortably below 1. Independent work by others landed in the same territory. The star was not carbon-rich after all. It was, chemically speaking, fairly similar to the Sun, and if the star is not carbon-rich, the debris disk was not carbon-rich, and the planet that formed from it is very unlikely to be a third diamond. So here is the honest version, which almost never made it into the follow-up coverage. The diamond planet was a reasonable inference drawn from a measurement that was later revised. Not a hoax, not a scandal, just science correcting itself in public, quietly, 3 years after the exciting part. The nickname survived anyway. It is still the first thing most people hear about this world. That gap, between what the field believes and what the internet remembers, is the real story here. But the planet did not stop being strange when the diamond went away. It got stranger. Go back to that orbital period. 17 hours and 41 minutes. To hold an orbit that fast, the planet has to be extraordinarily close to its star. Mercury orbits the Sun at about 36 million miles. 55 Cancri E orbits at roughly 1.5 million. Picture it this way. If you shrank the star down to the size of a basketball, this planet would be circling it about 2 inches above the surface. At that distance, tidal forces almost certainly lock the planet's rotation to its orbit. One face permanently toward the star, one face permanently away, no sunrise, no sunset, no day cycle at all, just a fixed, unmoving sun burning in the same spot on the sky, forever. The dayside temperature has been measured repeatedly. Estimates cluster around 2,400 Kelvin, with some measurements running higher. In Fahrenheit, that is somewhere in the neighborhood of 4,000 degrees. Let that land. Iron melts at about 2,800 degrees Fahrenheit. Steel forges run cooler than this planet's surface. The dayside of 55 Cancri E is hot enough that rock itself does not behave like rock. Silicates melt. The surface, if there is a surface, is very likely an ocean of liquid magma. And this is where the comparisons get genuinely difficult, because we do not have an Earth analog for a permanent hemisphere-wide lava ocean. The closest thing is a volcanic lava lake, and those are a few hundred feet across. Here, the lava lake is a planet, 40 light-years, 17 hours and 41 minutes, 4,000 degrees. Hold on to those 3 numbers, because everything that follows is a consequence of them. In 2016, Brice Olivier Demery and colleagues published a thermal map of the planet in the journal Nature, built from Spitzer Space Telescope observations. A thermal map of a planet 40 light-years away. We cannot see the planet, but we can watch how its heat signature changes as different parts of it rotate into view across an orbit. Reconstruct that, and you get a crude map. The map showed something the models did not predict. The hottest point on the planet was not directly beneath the star. It was offset, shifted to one side. On a planet with a thick atmosphere, that offset is easy to explain. Winds carry heat downwind before it radiates away. But this planet was supposed to be a bare rock, stripped of atmosphere by that ferocious stellar radiation. A bare rock should be hottest exactly where the light hits hardest. There was also an enormous temperature contrast between the day side and the night side, a gap of well over 1,000 degrees. That pointed toward poor heat circulation, which pointed away from a thick atmosphere. 2 clues, pointing in opposite directions. And there was earlier evidence, from Demery's team as well, that the planet's measured heat output had varied substantially between observing campaigns. The dayside emission was not steady. It appeared to change. Researchers still cannot fully explain that variability. The leading candidates involve volcanic plumes, or clouds of vaporized rock forming and dissipating, or a partial atmosphere being repeatedly stripped and replenished. Every one of those is a hypothesis, not a conclusion. What we can say is this: something on that world is changing on timescales we can watch. 40 light-years away, and it is not sitting still. In May 2024, a team led by Renyu Hu at NASA's Jet Propulsion Laboratory published results in Nature from the James Webb Space Telescope. They used 2 instruments, NIRCam and MIRI, to catch the planet's secondary eclipse. That is the moment the planet slides behind its star and its own heat drops out of the total signal. If the planet were a bare rock, the day side should have measured extremely hot, and the spectrum should have been featureless. It did not. The day side came in cooler than a bare rock model predicts, and the spectrum showed absorption consistent with carbon dioxide or carbon monoxide. The interpretation the team put forward is that 55 Cancri has an atmosphere, not an original one. The star would have stripped that away long ago. A secondary atmosphere, continuously outgassed from the magma ocean below. Rock melts, releases dissolved gases, and those gases replenish an envelope that the star is constantly blowing away. A permanent atmosphere, in permanent resupply, over a permanent lava ocean. This is the first credible evidence of a substantial atmosphere on a rocky exoplanet. And the researchers themselves were careful. The signal is at the edge of what is measurable. Alternative explanations have not been eliminated. Follow-up observations are ongoing, and some subsequent analyses have argued for more caution about how firm the detection is. That caution is the point. This is what a real frontier looks like. Not a headline. A measurement that is almost too faint to trust, being tested by people who are actively trying to break it. Here is why astronomers keep pointing telescopes at a world where nothing could ever live. Rocky planets around other stars are the whole game. They are where the question of life gets decided. And the single biggest obstacle is that we do not know whether small rocky planets in these systems can hold on to atmospheres at all, or whether their stars simply strip them bare. 55 Cancri is the extreme test case. It is the worst possible environment. Closest orbit, highest radiation, hottest surface. 17 hours and 41 minutes per orbit. 4,000 degrees on the day side. If a planet in that situation can maintain an atmosphere by outgassing from its interior, then the outlook for cooler, gentler rocky planets improves considerably. There is also the magma ocean itself. Earth had one, roughly 4.5 billion years ago, after the impact that formed the Moon. Every rocky planet is thought to pass through that stage. We have never been able to observe it. Now we may be watching one, continuously, in real time. A frozen snapshot of the phase our own planet went through before there was any ground to stand on. That is worth more than a diamond. And it is worth being precise about, which is why it matters that the diamond story got walked back, and the atmosphere story is being tested rather than announced. So what happens next? More JWIS time. The atmospheric result is the kind of finding that demands repetition, and 55 Cancri is now one of the most heavily requested rocky planet targets in the sky. Additional secondary eclipse observations through the rest of the 2020s should either firm up the carbon dioxide signal or dissolve it. Beyond that, the next generation of ground-based telescopes comes online. The extremely large telescope in Chile, with a primary mirror over 39 meters across, is expected to begin operations in the late 2020s. Instruments at that scale can attempt high-resolution spectroscopy of planets like this one, potentially resolving individual molecular signatures rather than broad absorption humps. And the variability, the changing heat output nobody can fully explain, will need long baselines of observation to characterize. That is years of monitoring, possibly decades. Meanwhile, the planet does what it has been doing for billions of years. 17 hours and 41 minutes, over and over. Roughly 500 orbits per Earth year. Something like 5 billion completed since it formed. It will keep going long after everyone watching it is gone. The star will eventually swell and consume it, but that is billions of years out. On any human timescale, nothing about this world changes. The only thing that changes is how much of it we can see. So what does all of this actually add up to? A planet got famous for something it probably is not. The diamond was a careful inference from a number that turned out to be slightly wrong, and the correction never traveled as far as the claim. That happens constantly, and it is worth noticing when it does. What is left is stranger anyway. 40 light-years away. A year that lasts 17 hours and 41 minutes. A surface at 4,000 degrees that may be an ocean of molten rock, breathing out an atmosphere as fast as its star tears it away. And 55 Cancri is one star. There are hundreds of billions in this galaxy alone, and the overwhelming majority of their planets have never been measured, never been named, never been looked at once. We found this one because it happened to pass in front of its star, from exactly our angle, at exactly the right moment in history for us to be watching. It is genuinely worth wondering what the ones we cannot see that way might be hiding too. If you want more of these, subscribe and turn on notifications. Everything here is grounded in real published research, rather than exaggerated headlines, including the parts where the research changed its mind.